Alright, so we're going to jump into Chapter 5 here, which is in Unit 4. That covers Chapters 5 and 6. So to start out, we're going to 5.1, the idea of probability. We're going to talk about simulation that goes along with that. So looking at our big ideas here, the probability is long run of relative frequency. Okay, it's always between 0 and 1. Okay, the probability is always between 0 and 1. In other words, 0 doesn't happen, 1 is going to happen, right? Short term, unpredictable, and long term would be predictable, okay? So long run for relative frequencies, okay? So if you do a long term setup where that's predictable, if it's a short term, it's kind of unpredictable. In which case, then we'll jump into the law of large numbers, which is definitely a key thing to really remember. If we do something many, many times, the proportion of desired outcomes will approach its probability. Okay, so we do something many, many times, the proportion of desired outcomes will approach its probability. That's the law of large numbers. So many, many times. That'll come into play quite a bit. You'll see questions referring to that. We're talking about simulation as well. So imitation of chance behavior based on a model that accurately reflects the situation. Example, using dice, flipping a coin, a random number generator. Things like that will be used for a simulation, which we've already kind of touched on a little bit, but again, we're going to touch on it again, okay? So the simulation process, describe how chance device imitates situation, okay? So describe how chance device imitates a situation. Then we're going to record results many times and use those results to answer questions, okay? So if we do this, these simulations, many times actually comes out to be a lot better setup where we get our bell curve and more predicted setup overall. The simulation process is more accurate by doing it many times, and therefore the results that we get are acceptable to answer the questions that are asked. Alright, so we're going to work through a couple of problems here to really kind of explain these best, so hopefully that makes things a little bit more easier to understand. So to start out here, we have Pedro drives the same route to work on Monday through Friday. His route includes one traffic light. According to the local traffic department, there is a 55% probability that the light will be red when Pedro reaches the light. Interpret the probability. So with this, the probability, it says 55% probability that the light will be red. So in other words, what it's saying is if Pedro drives to work many, many times, about 55% of the time he will hit a red light. Okay, so again, that's dealing with the law of large numbers, right? If he drives to work many, many times, about 55% of the time he will hit a red light. So in this situation, they already gave you the probability, and we're just wanting to interpret what they're talking about. Alright, so again, if Pedro drives to work many, many times, about 55% of the time, he will hit a red light. Now, part 2 here, probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow with each statement. Explain your answers to your neighbor, okay? Well, we're going to just explain this overall since we're not in class. So for A, it says the outcome is impossible. It can never occur. With that, we're going to simply have 0, right? 0 is saying that it's never going to occur. The probability of 0 is saying it's never going to occur. So therefore, the outcome is impossible. It can never occur. So again, it says it can never occur at 0. For part B of number 2, this outcome is certain. It will occur on every trial. Well, if it's certain and it's definitely going to occur on every trial, then it's going to get a 1 because that means it is going to happen. The probability of occurring is a 1. It's 100%. It's going to happen. So 1 is the answer for that. For part C of number 2, this outcome is very unlikely, but it will occur once in a while in a long sequence of trials. So it's going to occur, but in a long sequence of trials. So out of the setups we have left here, up there, we've taken care of our 1 and 0. So with this one, since it's going to occur in a long sequence of trials, the best way to look at that would say that it was 0.001. Okay? So in other words, it will occur in a long sequence of trials. So now for part D of number 2 is, this outcome will occur more often than not. So with that occurring more often than not, we want a number that's going to be close to that 1, right? Close to that 100%. So of course you can see one of those numbers we have left is 0.99, so 99%. That would definitely be an option that we could use. And then another one that's close, right? That's above the median of it, right? So above the middle part of it. We're looking at 0.6. I would say 0.6 or 0.99 could be good probabilities that we could say that an outcome will occur more often than not. So we're going to go with 0.6 or 0.99 in this situation. So now number 3. A husband and wife decide to have children until they have at least one child of each sex. The couple has had 7 girls in a row. Their doctor assures them that they are much more likely to have a boy next. Explain why this doctor is wrong. So why do you think this doctor is wrong? Well, the probability is unpredictable with the short-term situation, okay? There's no way of totally determining the next one is for sure going to be a boy. The probability of the next baby as a boy is still 50%. It still could have another girl to give him 8 girls, or he has a 50% chance of getting a boy. It's still like a flip of a coin on whether or not he gets a boy or a girl. No matter what the doctor says, that's just him trying to reassure that he's going to get a boy so he can keep getting that insurance money for another baby. So in this case, it's truly a 50% chance, okay? This couple, the probability of their next baby boy is just 50%. So again, the way to write this out is simply saying the probability is unpredictable in short-term situations, okay? So again, as we talked about the probability at the beginning, for long-run relative frequencies, it's always between 0 and 1. Short-term probability is unpredictable, and long-term is predictable. In this case, it's a short-term. It is unpredictable. So the probability for the next baby to be a boy is still 50%. There is nothing written in stone that says he is going to definitely have a boy next baby. Okay, so for part 2 of 5.1, we're going to jump into simulation, where we talked about imitation of chance behavior based on a model that accurately reflects the situation. So examples of like dice, flipping a coin, random number generator, things like that, okay? As well as the simulation process, describe how chance device imitates the situation. In other words, it will record the results many times and use those results to answer our questions. So let's go into this and read this problem and see what we can figure out. So a basketball announcer suggests that a certain player is a streaky shooter. That is, the announcer believes that if the player makes a shot, the player is more likely to make the next shot. As evidence, the announcer points to a recent game where the player took 30 shots and had a streak of 10 made shots in a row. Is this convincing evidence of streaky shooting by the player? Assume this player makes 50% of the shots and that the results of a shot don't depend on previous shots. Okay, that's the key thing. They don't depend on previous shots here, okay? So here we go. So number 1 wants us to describe how you would carry out a simulation to estimate the probability that a 50% shooter who takes 30 shots in a game would have a streak of 10 or more made shots. So let's think about this. Probability 50%, right? What's an example piece of equipment that we could use to determine 50%, right? So we're probably, well, we could use random number generator, be fine. But something that's simple, if we want to do this really quick and easy, how about flipping a coin? You got a 50% chance of getting heads or tails, right? So let's go ahead and do this. Let's try and flip a coin 30 times, since it wants to do 30 shots. We'll flip a coin 30 times and assign heads to making a shot and tails to be a miss. Alright, so we're going to record whether or not there are 10 heads in a row and do this many times to estimate what percent of the time there is a streak. So again, we'll be doing this, flipping the coin 30 times. Then we'll probably get a little tired, but flipping the coin 30 times and seeing if this plays out to where he gets 10 heads in a row. Alright, so we're 10 made shots in a row. Alright, so we're going to flip a coin 30 times, assign heads to making a shot, tails to be a miss, record whether or not there are 10 heads in a row, do this many times to estimate what percent of the time there is a streak. So again, this isn't just flipping it 30 times saying we're done. Your thumb may be flipping that coin, I don't know, 120 times, right? 150 times to try and get that set up, because you're going to do 30 shots, right? So every group of 30 shots to see if you get 10 heads in a row, okay? So that's how that's being described as our simulation for that type of problem. Let's move on to the next one. So the dot plot displays the results of 50 simulated games in which this player took 30 shots, okay? So he took 30 shots. That shows you how many he made is in a streak, okay? Out of those 50 simulated games. So with this, explain what the two dots above 9 indicate. Well, what that is telling you, those two dots right there above 9 are saying there were 2 trials that resulted in 9 consecutive makes. So out of this 50 games, 2 of those games where he took 30 shots, he made 9 shots in a row. Okay, he made 9 consecutive shots. So again, there were 2 trials that resulted in 9 consecutive makes. So number 3, what conclusion would you draw about whether this player was streaky, and explain your answer? So with this, looking at it, we'd say from the 50 simulated trials, there was only 1 out of 50 that was a streak of 10 or more. So that gives you a 2% chance, right? Or 2% probability. So this means it is not likely to happen by chance. So the player is streaky, okay? So he's streaky. In other words, again, the 50 simulated trial, there was only 1 out of 50 that had a streak of 10 or more. So that was 2%. So with this, that means it is not likely to happen by chance. So the player is streaky. So again, from the 50 simulated trials, there was only 1 out of 50 that was a streak of 10 or more, so it's 2%. This means it is not likely to happen by chance, so the player is streaky. Now you may be thinking, that's only 2%, so what do you mean? Okay, so again, the 2% may be throwing you off at why you're saying that streaky, okay? Well, in this setup, the null hypothesis, in other words, the claim initially, right, is this player is just the average player. However, there is a claim, an alternative hypothesis that's being saying that this player is streaky. So again, we have our null hypothesis as far as being a normal player. The alternative is him being a streaky player. Now, to determine which one we agree with, we're comparing that to our significance level of 5%, okay? In this case, and we haven't talked about that much, but that's what the significance level we're always going to compare it to if it's not given to us. So, in other words, what this means is, if, in this case, the percentage is lower than 5%, which in this case was 2%, we're going to reject the null hypothesis and accept the alternative. So since he was only 2%, which is less than 5%, our significance level, we reject the null as far as him being a regular player, and we say he is a streaky player. So that's why we're saying it's not likely to happen by chance, so the player is streaky. If his percentage would have been 8, then therefore we would have accepted the null hypothesis by saying that this player is just the average player and is not a streaky player. Okay? That's what that's referring to. Again, your significance level of 5% is what you're going to always have in the back of your head. If they don't give you a significance level, you're going to use 5% to go off of to determine whether the player is streaky or not in this case, or whether the player is going to go with the null hypothesis or alternative hypothesis. So I know it's kind of jumping ahead a little bit. We're just kind of introducing that thought process because we will jump into that a lot more in detail moving forward. So I hope that explained a little bit today, and you learned a little bit more about probability and the simulations that we can use for that. I'll see you next time.